Hi and welcome. So you may have remembered, if you've been watching my channel for a while, that one of my last projects that took a considerable amount of time, 25 hours or so, if I remember right, I'm guessing at this point, but was to make a holder to weld this profile. So these are two pieces of stainless steel, 303 I think, 304 stainless, and they're getting welded in T configuration, and it's designed to fit the two pieces coming in this side, and then the weld laser heads come in on both sides. I relieved this large section, and then right after the weld it's further relieved so it does not rub. That was one of the many modifications we've done since we started these. Well, this project was massive, and this was the simplest profile. Now I need to do the remaining 7 of these for all these other profiles. I'm not even sure what profile goes in here, and these are interesting because they're made out of, one's made out of brass. I'm not even sure why they did that, but in any case, these are going to be really complicated. So first, I got to take all these apart and measure all these bits so that we can make them out of not stainless steel, so we can make them out of D2 tool steel, have them hardened so that they resist wear, because the parts that came with it, this is hardened D2 right here. And there's even a little wear you can see inside there. There's even a little wear on this guy, even being hardened to Rockwell 58 or something like that. I can't remember. Anyways, so it's a huge problem with wear, and so we need to make these things a little sturdier. And so the soft, mild steel that they made these out of is not going to cut it. So we need to do better. So that's why we're modifying these. And actually, if we had it to do over, this would be a complete redesign, and all of these parts would be spring-loaded because there's a lot of warpage going on. The moment the laser beams, plural, hit both sides of the part, it gets welded on both sides simultaneously, it starts to warp because it also cools very quickly. The heat's dumped in quickly, cools quickly, and the part starts to warp. And it curves one way and another way, just in this T one, which is symmetrical. These other ones, we don't even know what they're going to do because they are not symmetrical, these other profiles. So you've got this profile, this profile. These are like that's like a backwards number 1. That's like a number 1 profile. And this is sort of a asymmetrical cut profile. These are all going to be really challenging because they're asymmetrical and they're going to warp strangely, so they might jam up in here. Again, if we had spring-loaded holders and we designed this thing from scratch, we could work around that, and we'd be able to account for some of this insane warpage that's going to happen. And I don't know what these are going to do. They're going to do something different than this one, I'm pretty sure. And this one cupped this way and cupped this way. And they haven't even done the version of this where they add material when they're welding. Right now, it's simply melting existing material. But ultimately, they're going to have a wire feed in on both sides coming in with air blowing the debris out of the way. And, well, they're going to try and figure out how that's going to work because they haven't even gotten that far yet. So far, we're just at welding existing material. So adding more material is going to cause more shrinkage and possibly more warpage. So my project is to remake all of these internal parts on all of these guys in D2 tool steel, have it hardened, have it ground so that it's smooth and slippery, and minimize the friction coming out of this. These weld boxes are also in sets. So you notice this is J11 and this is J12. That's because the first step is to weld these two pieces together like that. And the next step is to flip that 180, have the flat part up here, and weld the bottom part on. And so the profile I have won't fit in the first one, so I can't even test it. And then the second one will hold the profile appropriately. And I can test that one, which is fortunate. This set here is actually 2 different profiles. These 2 do one profile. These 2 do a different profile. This is number 1. This is also number 1. This is S11. This is S21. And these profiles are very similar, and they're doing a similar profile to this one that you flip upside down for the final weld. So the first weld just does the T part of it, an offset T, because it's not really a T, it's held to one side. And same with this one here. Looks more like an L than that one does, actually. In case you're wondering, here's S1. So you see I can't even fit this in here because the first pass, I think, is just this vertical part and this T. Same with this one here. Is this vertical part and this bottom part. goes through. Then finally, it's flipped upside down, and then it's welded like this, which that one does fit. So fits in here like that. And then this one goes in this way, and I believe fits like this. It's got a big burr on the end, which I probably should take off, so this is tight enough it won't fit, but it goes like that, and this bottom part is welded on. So you can see, I can't test 3 of these, the die, to even know if I made them right. So I've got to get my measurements exactly right. So next step is take each one of these apart and measure everything carefully. The problem is that these weren't made on a CNC machine, and they sort of seem like they freehand drilled holes in a lot of these, because when I measured the other one, the one that I've done so far, the material, the holes weren't extremely close as far as like being symmetrical. So if you have 2 holes holding one part in, one would be offset by like 20, 30 thousandths, which is an awful lot. I don't know what was going on with that, but hopefully these will be better. But if they're not, then I have to be more careful with my measurements. After working with these parts a bit more, I think what happened was they made the parts probably fairly accurately with the hole positions symmetrical about the center line. And then they didn't fit exactly right for whatever reason. They took them to a belt sander and hand sanded them to fit. And so the amount of material they took off was obviously not the same on both sides. And as I went through all of these, this is in hindsight looking back, some of these were off by like 50, 60 thousandths this way. They were also off vertically by a fair amount, which lends me to think that they really weren't careful about making these, and maybe there was a lot of hand drilling involved as well. This makes it particularly challenging because their fit inside the upper part of the weld box that I'm not modifying is fairly tight. And so I'm going to probably have to make these and then adjust them after heat treating when they shift in size a little bit, which is going to be lots of fun with the hardened material. So taking this first one apart, the top piece, I don't need to remake this because they're using bearings to guide the very top. And there's 4 bearings, interesting. That's more than the other one, I think. In any case, so I don't need to worry about this top, so I can take this whole top piece off. And I got to be very careful to number and label these parts. So I think what I'm going to end up doing is grabbing a silver Sharpie and labeling all these. And they use a bunch of different size screws. These are all metric screws. And there's a whole variety of sizes, because why standardize? Okay, so 3 pieces are held in the top section, 2 in the bottom. That's very similar to the previous one. Mac, this one looks pretty much identical. And you can see, they've only run a few sticks through here, and you can see the wear already. That's why we need to go with hardened steel, although even hardened steel seems to be subject to damage from running these stainless parts through. Stainless is kind of abrasive. All the chromium in it can be problematic. Also, so this is J11. This is the side that faces the operator over here. So, again, this is J1-1. This is going to be, we're going to label all these on this side. This is the exiting side, so we're actually going to relieve the material of the new ones from the center this direction so that they don't touch. Let's see, so this is going to be number 1, this will be number 2, and this will be number 3. So this one right here will be number 1, that fits down in there. This will be 2, this will be 3. And this one will be top number 1, top number 1, top number 2. And we'll label those when we get those out. So for starters, let's pop these guys out of here. See? Different length screws. And as I recall, there's more than just a couple. different length screws in this thing. Okay. So this one is J102. And this is J. See, this one needs silver. They're all over the place. By the way, they're all covered in grease, which tracks the soot wonderfully. Makes them really fun to hold. That's why I'm wearing gloves. This is J103. And what I do is the parts that I make, in order to be able to have them protect themselves so I don't lose track of what's what, when I send them out for heat treating, obviously everything's going to change. So what I do is I laser engrave the new parts so that I know which part's which. Okay, so next this guy needs to come off. Wow. Okay, this one's this side. This one is J101. I think what I'm going to do is I'm going to call these 4 and 5. Top and bottom's too challenging, I think. So this one will be 04. This is 05. And they all reference this side of the weld box. So this one matches this one. This is J104. This relief and this relief are kind of strange. I think that's so that they don't rub on parts in the box here, but it's not necessary for part entrance. The part comes in here on this guy. So, wow, look at that wear. This maybe had a couple parts go through it as all. That is dramatic amounts of wear. And we got to come up with measurements for all these now. To get the whole height above the bottom, I measure around here. This is 0.314 diameter. It's a shoulder bolt like this, and they're somewhat precision ground, so it should fit pretty well. And then in order to get, so that gives me the height from here relative to the bottom of the hole, so this distance from here to here, but over the top of this, so I've got to divide 0.314 divided by 2 to get the center of that hole. Then I need this end here, so I was trying to figure out how I'm going to do that. It's got a mostly flat side there, so I've got a vise here, and I'm going to stick this guy so that I can get as much exposed as possible while still supporting the bottom. So we're going to just catch it like that, and we're going to come up behind it and try and make it fit without running into something, which is really challenging, it turns out. There we go. And I can't get any closer than that. I wish I could. Yeah. So it could tilt a little bit if the threads are not perfectly perpendicular, which I doubt they are. After measuring a bunch of parts this way, I ran across the issue that I wasn't being able to get repeatable measurements, and this was not ideal because I couldn't get in here very easily to measure this. So I got a larger grinding vise, as you can see here, And then instead of going this direction, I switched to the long direction, but then what was to stop it? The vise stops it from rocking side to side like this, but it doesn't stop this very much. I could lock the vise in any position I want, which would dramatically change that height, as you can see. So what I did was I took a gauge block off the bottom of the vise, and I held it tightly in here against the back and the side while I tightened it down, and then I was able to get repeatable measurements to within 1/1000th or 2 every time. Still not as precise as I would have liked, although this isn't that sort of project, but figuring out a way to do things repeatably is important to me, and this was only somewhat because, again, the bottom of these things are hand ground, so they're actually sitting at an angle, all of them. And that's really problematic. You see, this doesn't even sit up on its own, even though that's relatively flat edge. So, yeah. And just as a trick, I found a deal on eBay for a lot of 8 of these gauge blocks. They're all 850 thousandths gauge blocks. They were used, so they're not great for super precision work, but since I paid just like $4 or $5 a piece, I can use them in spacers and vices, and I also use them to set the height to 0 on this guy, just to verify that my height is correct on this guy, because you got to 0 this one, then 0 this guy over here. And if you don't do it correctly, then your measurements will be off. So I make sure I can get repeatable measurements there first. So I'm just leaving 2 of these gauge blocks over here, but this is a handy deal. You can find a group of the same exact gauge blocks. You're kind of set. Like I said, I got them for like $4 a piece or something like that. So that was pretty handy. And the grinding vise also, larger grinding vise, supported more material, which was also good. Helped me get more repeatable results. So after I went and did all of this, I had to go back and remeasure all these parts as I was preparing to make them, because I didn't trust those original measurements. Some of them were really close. Some of them were way off. It depends on how bad the hand sanding was on the end. Some of these were really bad, and they weren't even close to being perpendicular. It seemed like they had gone back multiple times just trying to get it to fit, and then they were done. One more observation I made is the amount of things they relieved were not really necessary. So this part, this is a number 4. So this part sits in the weld box like this, and this is the entrance. The part comes in here, gets welded somewhere in the middle, and then comes out the end here. So like this part here, this relief cut wasn't necessary, and all the parts have all sides relieved. So I didn't relieve this side when I made the new parts. This side and this side, this is not a 45, but should have been, because the material enters on this side of this part. So this didn't make any sense for the 20-degree chamfer, 25-degree chamfer that is. 45 would have been more accurate like this side. So I put a 45 here and a 45 here. This side has an entrance chamfer so the part can ease its way in. Also on the bottom, because remember, this is one of these vertical to horizontal mounting sections, so you got to allow room for the part to come in that way. And again, don't need any relief over here. And I did these sort of analysis on every single part, and then looked for where the wear was and adjusted appropriately. You can see on this one there's a nice scoring here, which not going to be able to help, unfortunately. That is where hopefully the D2, the hardened D2, will help. Just to show you how far off they are, this hole from the edge is 0.528 over the 0.314, so you got to divide by 2 and subtract half of that. So that's what, 150 plus 7, 157, so subtract 1.157. This one's 0.509 for the right, or the output and the input. So that's quite a huge difference. If I drilled the hole identically, it wouldn't line up. That's the crap I'm talking about with these things. They should have been more careful when they made these, and they could have made them all the same. Now I got to measure every single one. After spending a lot of time characterizing all of these parts, I went through every single weld box and characterized the part in the weld box, did all the measurements so that I could make every individual part. I also labeled them, because I'm going to have to laser engrave these so that I can figure out which part's which when I send it, after I send it out to heat treat, because the heat treat process will, you know, mix all the parts up potentially, and it would be a pain in the butt trying to figure out which one's which. So I'm going to laser engrave every single part with a unique part number. This would be weld box S1, part number 1, and on the weld box itself, I've labeled where 1 is. Then, and this S1, weld box S11, part number 2, 3, 4, and 5, etc. So then it was find the material time. And unfortunately, these parts, even in metric, they don't make sense. So these dimensions don't make any sense even from standardizing. So if I chose 130 millimeters, that'd be 5.118. It's not well under that. It's not 125 either. 125 millimeters, 25.4 divided by would be 4.92. It's not that either. It's not standard metric. It's not standard English. The thickness doesn't conform to any standard American dimensions, 0.792. So if you want 750 for 3/4 of an inch, this is slightly over an inch, 1.026. Let's see, 0.792. So let's see what 0.792 is close to in metric units. 0.792, 25.4 times would be 20. So it's not 20. So they would have to go for 25 millimeters, which is a lot, about an inch thickness. So they'd have to remove a lot of material even in metric because it's over 20 millimeters. You think you'd make it 20 millimeters since they didn't surface grind any of their parts. They're all rough, fairly speaking, just rough machined. So none of these dimensions conform to anything that makes any sense. Maybe the height does. 1.026. Let's see, 1.026. 25.4 times is 26. Now 26 millimeters doesn't seem like a normal size either. I'm not sure how it worked out. There must be a reason for it. I just don't know what it is. But because of this, I can't buy standard stock. So I can't buy 3/4 inch thick stock. I've got to go the next size up, which is 1 inch. Most vendors don't carry 7/8. It's very rare in D2. For at least the vendors I know to deal with. 1.026 means I got to go to at least 1 1/4, like McMaster only goes to 1 1/2. Online Metals, I can't remember. I think they had 1 1/4 in D2, but that requires me to remove a ton of material off of these parts in every dimension and then surface grind them. Well, the only parts that really need to be surface ground are the parts that are in contact with the moving parts, because we want it to be as low friction as possible. So I could reduce the amount of surface grinding, but it's still a lot of machining to get these parts to final dimension. My solution was to go with a company called Tool Steel Services. And not only are they a primary vendor for tool steel, but they also do surface grinding. So I bought my material pre-dimensioned exactly to size, which saved me a lot of trouble. So this is 0.79, like 0.792 or something like that. They're within a few thousandths is what they guarantee. And the width is pretty close to 1.024 if I remember the bars I looked at real quick. So I have saved probably 20, 30 hours of machine time just by buying this stock. Now, price-wise, that made the price jump a bunch. Compared to McMaster car, where I'd have to buy massive overstock size, it's about $80 a bar. The bars were 250 or 60 a McMaster car, something like that. And these were 365. All told, the customer was right there with me saying, yeah, let's buy it pre-dimensioned. It takes longer. I had to wait 3 weeks to get it, which they were not overly excited about, but glad that it's going to save them a bunch of money, because I bet you dimensioning time for all these parts, there's a total of 31 parts, I think. And I bet you it's 20 plus hours of time just dimensioning stock and whatnot, cutting, dimensioning, all that. I still have to cut these down. Now there's another problem. That 5.071 length, that 5.071 length, these are 36-inch bars. I can't, with saw allowance, I am probably like a ½ inch shy of getting 7 parts out of each bar instead of 6, which is such a bummer, because it's literally, because I need to get the ends to dimension, and so I have to leave a little extra on the ends, and I don't think with my saw I can get accurate enough cuts to actually get 7 parts per bar. I'm going to be left with a good chunk of bar left on each end, which is really sad. Like it's going to be 5 maybe 4.8, 4.9 inches left over on each bar, which is really sad. So interestingly enough, I asked Tool Steel Services how they make their surface ground bars to dimension like this, and what they do is they buy sheet stock. So they buy D2 sheet stock. I'm guessing, I don't know, maybe they can get in 7, they're a primary distributor in the United States, so maybe they can get 7/8 inch thick, but maybe, or maybe not, maybe they had to go to 1 inch. And what they do is they surface grind both sides of the sheet so that they're flat and parallel to each other at the first dimension, so in this case 0.790 roughly. Then they saw cut the sheet into strips to get the length bars, which is why I'm limited to 36 inch bars for the surface ground ones. And then they flip them over and they surface grind these sides to be flat and square with the other two. And you end up with dimension stock, which is going to save me a boatload of trouble, a boatload of effort. So next we're going to head over to the saw and we're going to cut these. And I'm going to see if I can get close to the 5.07 dimension. If I do 5.1, I could get 7 out of these, but that only leaves 29 thousandths, well, or less, depending on, these are all different lengths. That's the other thing, is they weren't very careful. These obviously were not, what do I want to say? These were not CNC cut. I thought these parts would have been made in the CNC machine, but I don't think they were, because they're very all over the place, and the accuracy is sometimes off like 20, 30 thousandths. I have to leave some allowance on the end, and I don't want to make them undersized, so that means that I don't think I'm going to be able to get 7. I'm just going to probably live with the 6, and we'll have a bunch of extra stock left over for something else in the future potentially. I did order an extra bar to allow for screw-ups. I ordered 1 extra bar, and the customer was fine with that, just so that in case something went wrong, we didn't have to wait. Over here at the saw, I've got a chart here that came from the saw manufacturer for surface feet per minute for materials. D2's on the previous sheet, and if you look down here at D2, it's 90 to 120 surface feet per minute, which is really slow. I had to increase the force a little bit on the blade. It's cutting at a reasonable speed here, but it's still, this is going to take a long time to cut out 30-some pieces. I put magnetic stops here so that I could repeat these cuts more quickly, but you got to make sure to get all the swarf out of the way so that it doesn't screw up your thickness, especially when I'm as close to size as I am here. Measuring, I gave myself 5.118, so that only leaves me roughly, what is that? Less than 30, so 25, so 35, 43 thousandths, so 20 thousandths aside to remove, which should be fine, hopefully. So we got to make sure to clean all that debris off before I slide it against my stop. By the way, my stop is a magnetic angle block, or magnetic mount here that I surface ground 2 of the sides on. I am using some cutting wax because this stuff is pretty abrasive. Here's the first stick. Got 6 oversized pieces. This is the leftover bit. This leftover bit is 20-something thousandths too small from nominal. That's it. What a freaking shame, man. If they could have given me like 1/4 of an inch longer on each stick, I would have been golden. So sad. All right, so here's all the pieces cut. One of the bars was a little bit long, and this one's 5.083, so I might actually be able to get a completely usable piece out of this. I just gotta be very careful when I'm skimming the ends, but I think that'll be good. These two are the odd sized parts, and I have to surface grind these because this is pre-hard D2, but it's rough sawn, and this is supposed to be 3/4 by 1 1/4. It's actually 0.8 by 1 and change, and so I'm actually lucking out here because I'll be able to get this to dimension, I think, because it's so oversized, although those saw marks are pretty deep in it. So I guess we'll have to play that one by ear, but I won't have to shim anywhere near as much as I thought I was going to have to. In this direction, it's quite a bit larger, and I was going to have to remove some material anyways for that. So we will do that. Being pre-hard, this is going to take a toll on my tool life. You can see all the pieces I've cut here. This is 29 pieces, and I got pretty consistent results if I didn't bump the magnets. I got to do a better stop on this because magnet stops This top is Blanchard ground and it's smooth enough, the things slide pretty easily. So if you slide in the part to meet up with the stop and you go a little too fast, it pushes the stop, which is not great. So anyways, we're within like 10 thousandths across the board here. So I'm satisfied with that. When I was being really careful, I was getting better than 10 thousandths, like 2 to 3. All right, on to surface grinding. Got these two pieces loaded up. So the thickness is large enough that I have about 10 thousandths of material I can remove. So I found the smoothest side. So we're just going to clean up this one side, flip it over, make it parallel. Hopefully it'll be around 790, but if it's a little shy, that's not a huge deal. And I'd show you the surface grinding, but that's kind of boring to watch, so I'll just bring you back when it's done. All right, so here we are at the end. The bottom got rough ground flat. The top, I didn't bother getting the edges because there was no need, because like from here over, it's going to be relieved anyways, down like 1/8 of an inch so that the material doesn't contact it. So that should be perfectly fine. Once it gets hardened the rest of the way, by the way, this is pre-hard. And because this stuff is pre-hard, it just wears my wheel out really quickly. And so I was taking like thousandths depth of cut each time, and I'd have to redress it after like every 5 or 6 thousandths kind of thing. That's why I left the diamond on the magnet, because it was just, what you can tell when it needs dressing, it starts burning like crazy. And you can't feel those, but there's some burns on the top here. Yeah, it burns across the whole thing and then cuts weird on the backstroke. So I learned really quickly that you got to redress the wheel constantly, which is just really crazy. This stuff's tough. I guess it's abrasion resistance, and we're seeing the abrasion resistance. Anyways, we got to take this over in the mill and mill this to the final dimension, thickness-wise, because these are extra wide. And then we can go ahead and proceed to laser marking. Turns out I could take some more material off here. Interesting, if you want to see where the wheel's wearing, look where the sparks are coming off of. That way you know how well the dress the wheel still is. You can see it's coming off the leading edge and it wears to the back. So it comes off the leading edge to the closest to me and then moves to the back as it wears more. Here's another pass. You can see that the wheel's still got some life in it with this dressing. So we need to square this up the rest of the way. We're going to do a 30 thousandths pass, see if I can clean up this whole side. Then we're going to flip it over and square up the other side. This thing is just very lightly sitting on parallels, mostly squeezed between the parallel faces, so hopefully it's sitting nice and flat. This material's pretty hard. That was 30 thousandths pass. That was a bit much at that feed rate. All right, next up we want to mark all of the parts so that I know after they've been heat treated which part is which, because that'll be a problem. So we're going to laser engrave them over here. So depending on what angle you're on, it's easy to read or hard to read. I don't know if the filled in text is exactly the way to go. I think I could just do outline and it'd be more legible. It really depends on what angle you get, because some angles it's extremely readable. I don't know if you can see that or not, but it'll definitely make it easier. And this is into the material. You can actually feel it, so that'll be great. I built these fences on my 3D printer. I printed them on my 3D printer. I bought some tool steel, but I didn't have time to make these, so these were a good solution. Each weld box gets a complete set of inserts, and they're all different. Although between weld boxes, like number 1 in each weld box, they tend to be pretty close to the same. They are not identical. Screw holes are moved over by 20, 30 thousandths. I don't know why they weren't more consistent, but definitely need to mark them. This doesn't look that deep, but it can actually catch it with my fingernail. So they're reasonably deep in there, and I think that last time I did this, they survived heat treat just fine and were easy to identify the parts after, so that's why we did this. This part here, along with a couple others, the pre-ground stock was a little bit large in the one dimension, so on 3 of these I have to reduce the size down. I did some test engraving on the sides of these guys, because I knew I was removing all that material, and everything above the line's coming off anyways. So I'm gonna, these all are the same dimension within 1/1000th. So I'm just going to take these over to the mill, machine these down to dimension, and we can continue on. All right, next up, we're gonna cut the width of each of these guys. We're gonna clean up the edges and get the width to size. And they vary in size a bit if you look down this list. But what we're going to do is we're going to go in each group, go for the smallest size and make them all that size. A few thousandths isn't going to make a difference, and they're all pretty tight to begin with. So we're going to do that. So like in this group, we'll do 71 for all these, or maybe 73. I don't know, we'll have to, what I'll do is I'll look at each weld box individually and see how they fit. I know some, I put asterisks next to the one that their excursions from nominal size are way off. 5.063, 5.050. That is a huge amount. It's 25 thousandths undersized. So if I send them to heat treat and they're large, then when they come back, I'm going to have a problem. Plus, this one screws to the top. So we may have to like do individual sizing for these really weird sized ones. Yeah, 4 and 5 are the ones mounted on the top, and they're just held in place by screws. So yeah, it may be a little more than just go across the whole set. These two, the top are the same as 71, so we're just going to do 71 across the board for the first set. We'll have to be very careful with each individual set. I do have drawings for every individual part in the whole thing, and I will use those as references when I go to make them. To square these up evenly, I'm going to use a square off my vice jaws here to line up the backs. We're going to take a skim cut off one side, flip them 180, and that will be the final size. We're going to take it to dimension. First up, we're just going to try and clean up all of the faces. This is a 3/4 inch solid carbide end mill, and still there's deflection. I don't know, probably not the end mill deflecting as much as the whole rest of the machine. This is pre-hardened D2, so it's like Rockwell C20 kind of thing, and it's pretty hard on the cutting tools. That's why I'm going straight to solid carbide. I had a high-speed steel, but I didn't think it would last. Even a 10 thousandths cut over an inch, 10 thousandths cut over an inch thickness engagement is a little bit challenging for this. You hear the chatter. 5.0715. I made it just a little bit over. That's dead on my DRO reading, so I guess we're going to go with that. We'll move on to the next set. I don't need to show you all these. It's going to be very repetitive, and because this material is so hard, it's loud and obnoxious. All right, so here's the first weld box in the next set. This is J11 with the 5 pieces inside that I have to make. Here's my blanks. J114, J115, this is J115, J114. Start with the easiest ones. And these have to be modified because we actually want to allow access, just like this part here. See how that matches up? We actually want that to go all the way from here over to here. So a lot more material removed in the replacement ones. Also, since the wear is right here, after the midline of these parts, we want to relieve that wear surface so that it doesn't make contact anymore on all of these faces. So all three of these parts are going to get relieved. I could just turn these two sideways, that one like that, and just come across all three at once. And that would work for the relief, and I'm doing 100 thousandths relief. Then I've got to do these two, the outer two, need to be relieved from like here to here, down whatever that depth is. I have individual drawings for every part. They should be pretty close to the same. Let's see. So J11, I don't think I caught the depth on that one. And J13, I didn't, oh, 0.905 from 1.023, so looks like about 125 thousandths on that one. Oh, there's 0.907. So again, about 125 thousandths. So we can just do 125 thousandths. It doesn't have to be exact because these are just relief pockets for the tool, the laser, to get in here. So there's going to be the laser in the middle. There's going to be air blowing this way and a wire feed on this side, and they're going to come right in the middle. So that's about where it's going to sit. I don't actually have the tube anymore because they needed it back. I guess I could knock out this part first. I'm trying to figure out how to do as many pieces at the same time without accidentally hosing myself by making a mistake and then wasting material, which would be horrible because it's very expensive material. So I just want to get it right. I think 1 and 3, and we'll do the relief from here to here. I think that's what we'll do for starters. Then I can do 1, 2, 3 and do the relief down the middle. This guy's already the size. And then I don't need a chamfer that side, but this has to be chamfered. That's an entry, that's an entry, and that's an entry. So all of those need to be chamfered. And you'll notice that the exit is towards me, exit is towards me, exit is towards me. That's why I put that on every part, because it helps you get your orientation right. Like the chamfers here, they don't make a sense. I think they just duplicated all the parts. The corner chamfers can make a big deal on how they fit inside this because they didn't make those relieved inside there. So I am going to need the outside chamfers. On the previous parts I made, I took these over to the belt sander. On these, I'm not sure. I might just stick them with an angle block and run through them real quick. We'll have to see when we get there. So I guess we'll start with 1 and 3. So we know where our center is. That's where we're at right now. And we're going to cut a relief cut. I think we're going to try 50 thousandths for start. I think I can do 100 thousandths with this cutter. The individual inserts are set at a negative rake, but they're positive rake inserts, so they don't take a lot of power from the mill. So hopefully that can be a thing. Let's try feeling it manually here. That's not bad at all. All right, let's try it the other way. 0.7. Even a 25 thousandths pass was having some issues. I might have to switch to a different face mill. This is an Iscar too. This is an expensive face mill, but just doesn't like this pre-hardened material. Maybe it's the insert geometry, I don't know. The plain triangle ones I have work better. Yeah, I don't get it. This face mill is doing a lot better. Doing the relief section now. 25 thousandths pass. I could have actually done one more piece in here at the same time. I blew it. Could have done 3 at the same time and gotten more work done. The center one also needs to be relieved the same thickness. We're drilling and countersinking holes, and I almost got caught in a really bad mistake because I've relieved this side but not this side. The holes are supposed to be centered between the big section, not the relieved section. If I hadn't been doing this, so I've got a ground pointer here that I'm putting in here. And I'm taking the original part and I'm dropping this down, which centers it in the hole, and then I can feel how close it is, and that's right on the money. But before I had compensated for this 100 thousandths relief, it was way off, and I go, well, I don't understand why it's way off, and I go, uh-oh. You can't get your center from here, you have to get your center from over here in the wide section. That was almost a huge faux pas right there. For this project, I've made a few tools just to speed things along. For starters, I made these 2 D2 tool steel tap guides, and this stuff's pre-hardened, so they're pretty hard and they work pretty well. I originally started with the outside dimension here of the tap, so this lines up very nicely and it's a very nice fit and really has good alignment. However, when you're starting, it still has room to go back and forth, as you can see there. So then I thought, well, maybe I'll make it for that dimension there. But then I have the problem where this won't fit any longer. So I have to unscrew this and then finish the threading after I remove the tap guide. But that's okay. This was a pretty decent use and I've already used it a bunch. Next up, if you watched my previous video for making these things, I've got these angle blocks that are designed to hold these parts. One angle's 40. It's a total of 90, but one's offset by 40, one's offset by 50 degrees. You notice that lies flat, so when I need to machine these slots for the length of this part coming up, I can use these angle blocks. They're all pinned together, and so you can actually spread them apart. And so you can push 2 of the pins one way, 2 of the pins the other way, and you can actually get these pretty decent way apart and then support the part nicely for machining. Finally, I got this guy here. We have to do a bunch of chamfers. So I'm doing a 45-degree chamfer one way. It'll hold these parts like so. And for the back end of these parts that fit into corners, I got a chamfer at 45. So I'll just make the vice jaw hold a 45 that direction. The other ones are lead-in chamfers, and they need to be at 25 degrees. So we're going to hold the part something like this over here. And we're going to make those next. So right up next, we're going to make this tool here so that I can do all the chamfers lickety split. I do have 31 of these to do, so there's a lot of chamfers, so it'll be worthwhile. So I want to take this jaw here, and I want to put slots in it that will allow me to hold the parts at angles. If I had a CNC mill, this would be a trivial operation. But without that, and I don't have a rotary base for this guy, holding this part at 22 degrees or 45 degrees is going to be really challenging. So this is a scale drawing, and this is where the center of the holes line up. So this is my plate here, and I could potentially hold this guy from the outside, except that it would be challenging to hold it so that the slots don't get in the way. I mean, hold down clamps is a possibility. You know, I was just thinking that maybe that'd be too hard, but so what I was going to do is I was going to drill and tap holes, which are on this drawing here, that would allow me to mount this at the various angles here, but maybe I don't need to do that. This is what the part's going to look like. So there are the slots, and they're shifted so I can maximize. The 22-degree angle gives me the maximum amount. The 45 is the same no matter wherever you put it, but if I shift this over, I got more out of the 22-degree angle, so that's good. And once it's at an angle, I can find a corner, which is a little bit of a trick, and I'll show you the tool I had made so that I could find that corner. Then I just do offsets from this corner, and that gives me all the slot location, you know, where to do my slot. So when this part is mounted 25 degrees, then it just becomes a horizontal milling operation. Same with mounting the part at 45 degrees, becomes a horizontal milling operation. Makes it much easier, right? All right, so over here we have a parallel angle block, 45-degree angle block, clamped on this side and screwed down through the center with washers on that side. Makes a really sturdy holding setup here. So now we can just mill out the material we need to mill out. Fantastic. Oh, before we do that, we got to find this corner, because all the dimensions on this drawing are referenced off this corner. Well, it's chamfered, so how would you find that corner? I'll show you a trick. The solution to finding this corner accurately is in this little tool that I had made. Both this plane and this plane go right through the center of this 1/2 inch diameter cylinder. So if I mount this guy along the side here and I bring my edge finder up and touch off this side and find the high point, I will be exactly 1/4 inch from the actual point if it existed. And then coming from the top down, same thing, find the high point, and I will be within 1/4 of an inch of finding the high point again. That's pretty good. So now, once I've got the one direction, I can come over to 0 here and come straight down, and I should be at the high point. Well, I will admit that finding this corner with this tool was a possibility, but it was a little fiddly. It was pretty hard to do. And the reason why is because you can make contact sort of over quite a few thousandths side to side unless you're really being careful. And this is parallel. And if the part sides aren't really parallel, then that makes it kind of problematic, because the bottom, if it's at an angle like this, the bottom will touch first before you ever get there. So what you want is to hit the high spot in one direction and the high spot coming in the other direction. And when you find the first direction, you should be able to go over the distance to the corner, which is half the diameter of the edge finder, which is 100 thousandths, plus another 250 thousandths, or a total of 350 thousandths over. So then you go to 350 thousandths this way, and that should be the high spot here as well. And it came within like 10 thousandths. It was kind of hard to do until I iterated a couple times. I got the pointer, looked at where the pointer would be, and then tried this again with the edge finder, and I got there. But I thought it was going to be easier, and maybe there's a trick to doing a better job with this. I'm not sure what it is at this point. One more quick comment is that without an electronic edge finder, the approach I'm using here would be almost impossible, trying to find this edge here like this, because you're trying to find the peak, and so the rotating part's got to touch on the very slightest edge, and it would be very hard to find. With an electronic edge finder, you can get very close. The way this is designed to work is vertically, and then you've got the whole length of this cylinder just has to contact somewhere, and you don't have to find a high point. That was my problem here. So here in that solution, you're just finding a high point no matter what the angle is, like this, you see? And that's easy to do. You just, somewhere on this cylinder has to touch the somewhere on this cylinder, and that's the high point, and 1/4 inch from the center. Well, the center of this is 350 thousandths from the center. However, what I was doing here was this direction. And so for starters, if this part is at an angle, you're kind of hosed because the bottom will touch first. If you're trying to meet the peak of one cylinder, meet the peak of another cylinder, that's a pretty hard thing to do to find the high point, because this indicator is really gonna want to light up over like 10 or 15 thousandths space across the surface. So what I did was I found one end and then the other end, and then I averaged the two and went to the middle and see if it really was kind of there. And that really was sort of the peak, and that's how I ultimately found this point. But it was fiddly, but this tool is not really designed to work in this direction. It can, it's just a lot harder to use. All right, so we need to go in until we get to 0.370. And we're coming out. Still got to clean up the corners here, but there's a nice fit. Held at a 45-degree angle, run a chamfer. All right, we got our angle set up for the next one, 25 degrees. That one's gonna come through here and go over to here. And same depth. Again, it's all gonna be based off this corner, so I need to find that corner very accurately. Clamping the tool in place helped me find my 0, 0. It took a bunch of iterations back and forth, but I got there. Definitely challenging, not ideal. Going 3.476. All right, very good. Next up, 45s. You can see it's not really holding on the main part, it's just holding on the bottom. So what I'm going to do is I'm going to stick a parallel in there so I can actually hold on more of the material, and that will support it better so that I don't get potential slippage. Still a big long lever arm out here,